Okay, so it's a pleasure to introduce Zheng Liu from University of California at Santa Barbara, who will talk about p-adic families of Yoshida lifts.
Thanks for the invitation and the introduction. We're really happy to have the opportunity to speak here. So today I'm gonna talk about an ongoing joint work with Ming-Lun Hsieh about p-adic families of Yoshida lifts. Okay, so first let me start with some background. So the Yoshida lifts was first considered by Yoshida in his 1980 paper. So we're going to start with the pair of Caspidal eigenforms on GL2, generating an automorphic representation pi1, pi2. So we're going to assume that they have the same central character. So in particular, that means we're going to consider when they have the weights of the same parity. And also we need to consume that we need to assume that there is a quaternion algebra over Q such that the pi1 and pi2 both have Jagiellon length transfer to that quaternion algebra. And so we do the Jagiellon length transfer, then we get a pair of automorphic forms on the D cross, the quaternion algebra. And this quaternion algebra D can be viewed as a four-dimensional Q vector space equipped with the quadratic, non-degenerate quadratic form defined like this, where the star stands for the involution for the quaternion algebra. And then the two copies of D cross will act on D by this, and this will induce a map, and this action actually preserves the quadratic form. So it's gonna induce a map from the two copies of D cross to the orthogonal group attached to this four-dimensional vector space over Q. So then we have actually induced an isomorphism from the quotient of D cross times D cross quotient by torus isomorph to this GSOD. So it's gonna be the connected component of the similitude orthogonal group of the identity. And now, so then with a pair of forms on D cross with the same central character, actually we're gonna get a form and an automorphic representation of this similitude orthogonal group. So we're gonna also extend by 0 from the GSO to GO. And then we're gonna do the theta correspondence from this orthogonal group to the symplectic group GSP4 and get an automorphic representation there. And this automorphic representation is actually the Yoshida lift. And in terms of Galois representations, we know that this Galois representation to attach to this Yoshida lift. So the standard one, the 5-dimensional one, is actually the trivial representation, direct sum, the tensor product of the Galois representation attached to pi1 and pi2. And the spin representation, the 4-dimensional one, is simply the direct sum of the Galois representation attached to pi1 and pi2. And we see we have this decomposition here. And from this decomposition, we see that this congruence between the Yoshida lift and the other stable representations on GSP4 can be used to construct Selmer classes for the representation, the tensor product of the representation attached to pi1 and the pi2. And actually, this congruence has already been started by several authors like Jia and Bocherer, Dummigan, Schulze-Pillot, and Agor-Clausing, and Hsieh Namikawa. So, they considered the congruence of the Yoshida lift and other forms, and then try to deduce some cases of Bloch-Kato conjectures for this tensor product under some certain assumptions. And today, what I want to talk about is to also what they worked with a fixed form and the full level at P. And so today what I'm gonna say something about is the picture of families. So we want to consider the Yoshida lifts of Hida families. So I have F1, F2, two Hida families on GL2. And so maybe for some technical reasons, maybe to also assume their square free time level. And so I use an underline to denote families. And so we want to consider the theta lift. So if we just want to do the theta lift of eigensystems, then it's kind of straightforward because we already have the result here. So we know you just take the eigensystem and you form the direct sum, and you will get the eigensystems, the families. So this is a bit like the case of Eisenstein series. So if you want to consider the Eisenstein family of eigensystems, also it's kind of very easy and straightforward because you know it's just some direct sum of something. And but for applications, so for example, for like studying congruences, actually you really want a family of actual forms instead of just eigensystems. So that's what we want to construct here. A family of Ziegel modular forms on this GSP4. And so we're going to assume that D, the quaternion algebra splits at P and is also definite at infinity. So we're going to consider the orthogonal group is going to be positive definite. And we want to construct a Hida family of Ziegel modular forms on SP4, interpolating the Yoshida lifts of the specializations of these two given Hida families. Okay, so we're gonna view the families of p-adic forms as measures over ZP cross CP valued in the space of p-adic forms. So we consider measures of, so they are viewed as measures over ZP cross CP is because the rank, actually the rank of both the orthogonal group and the symplectic group. So the SP4 and the O4, they are both of rank 2. So therefore the weight space, the natural weight space for this, for p-adic forms on them are both dimension 2. So they're gonna be correspond to characters of ZP cross times ZP cross. So we're gonna have, so by the definition of the Yoshida lift, actually the theta lift, so we need to have a theta series, which is an automorphic form on the product of the orthogonal symplectic group. And then we pair it with the form on the orthogonal group, and then to get the form on the symplectic group. And so here we consider the space of p-adic measures. So what we want to do is, so in this first space, the families on the orthogonal and the product of orthogonal and the symplectic group, we want to construct a family, a p-adic family of theta series. And on this second space is the families on the orthogonal group. So we already have the given one. So the Jagiellon's transfer of the form families on GL2 to the quaternion algebra. And then given these two space, if we use the convolution of p-adic measures, and then it's going to produce another measure on ZP cross ZP. And then on these two copies of p-adic forms on orthogonal groups, we're going to use the p-adic Peterson inner product to get a scalar, and then we get a map to this space, which are the families of Ziegler modular forms on GSP4. So we're gonna get our family of Yoshida leaves here. So therefore, from this picture, we see that what we need to construct is really something here to pick Schwartz functions to construct a bunch of a bunch of data series and interpolate into a family. Okay, so next I'm gonna talk about the construction of this family here, especially the choice of Schwartz functions at the place P. So first I'm gonna rewrite this space in another way, so it's more convenient to do p-adic interpolation. So we know that the p-adic forms, so we know the orthogonal group is definite, so the Schmurl variety is gonna be a bunch of points, and the p-adic forms is gonna be some continuous functions on a set of points. So we can rewrite as a continuous functions here like a quotient of the finite adelic points of this orthogonal group. And then we can switch the measure and the continuous function, and we reach this space. So this is a continuous functions on those points such that the set of the continuous function on a set of points valued in the measures with values in p-adic forms on GSP4. And by the Q expansion, we also know that the p-adic forms on GSP4 is actually a closed subspace of the Q expansions. So we're gonna embed this space into the following one. So here, this one will replace the space of p-adic forms by Q expansions, and also we know that the measures over ZP cross ZP actually is gonna give me something inside the Iwasawa algebra of ZP cross times ZP cross. So actually, this measure space in the measure of this space here is actually gonna give me something like a lambdatic Q expansions. So in the end, we want to construct something which are continuous functions on a set of points with values in lambdatic Q expansions. So we want to interpolate those Q expansions. Okay, so what we need is to kind of pick. So we want to pick Schwartz function. Phi kappa 1, kappa 2, where this kappa 1 and kappa 2 are points of the weight space. And we are gonna interpolate the classical form. So we're gonna only consider the classical weight. So we're gonna, the kappa I is gonna be a product of a finite order character and an algebraic character. So here I assume K1 is strict larger than K2, larger or equal to 2, and the chi is finite order. So we're gonna pick suitable Schwartz functions and interpolate the corresponding Q expansions of the theta series. So since we want to interpolate the Q expansions, so let's first see what's the formulas of Q expansions of theta series in terms of the Schwartz functions. And actually, they're kind of relatively easy. So, I mean, easy for p-adic interpolation. So given a Schwartz function phi on these two copies of quaternion algebra, and I will assume that the infinite part is a polynomial function, so algebraic part times the standard Gaussian function. So here I write the x as x1, x2, so two copies of D. And this parenthesis x comma x is the 2 by 2 matrix given by the quadratic form. Okay, then the Q expansion. Then the Q expansion of this theta series at a point of the orthogonal group is given by this following formula. So the Q expansion is indexed by symmetric 2 by 2 matrices, semi-definite symmetric 2 by 2 matrices, and then for each this index, the coefficient is a finite sum of rational points whose matrix for the quadratic form is beta, and then takes the value of the algebraic part of the Schwartz function at the G inverse times x, and here the algebraic part is the Schwartz function at all the finite places times algebraic part of the Archimedean place, and this formula is kind of very easy to get from the definition of the theta series and the standard formulas for the V representation. And okay, so now we have this formula here. So we want to have, once I'm given the classical weight, kappa 1 and kappa 2. So I want to pick this Schwartz function kappa 1, kappa 2 such that the value of these Schwartz functions at a point x actually is interpolated by a p-adic measure on ZP cross times ZP cross when the kappa 1, kappa 2 vary in the weight space. So that means I'm going to interpolate each terms here to get a family of Q expansions. And also what I'm going to do is, what we can do is, I'm going to choose the sections away from P and infinity. I'm going to fix throughout the family. And the section at P is going to depend on the finite order part of the weight, and the section at infinity is going to depend on the algebraic part of the weight. Okay, so any questions? Okay, so that's what I want to do. And actually, in order to pick the Schwartz function, so we can interpolate it here and to get a family of theta series, is something that is not kind of relatively easy. So for example, we can easily make many examples. So I can consider if I write this x in the coordinates, so 4 by 2 matrices. So and for example, a very easy choice will be, I want the section at P to be supported on the integral points. And I want the x11 and the x22 to be supported on ZP cross. Then I take the value of chi1 at x11 and then the value of chi2 at x22. And for the infinite part, I can just simply take the x11 to the k1th power and x22 to the k2th power. And now if you look at these two parts together, if you combine the contribution from P and contribution from Nakimian plates, you see that this is actually the value of x1 kappa 1 at x11. So therefore, this certainly is going to be interpolated by the p-adic measure, which is a delta measure at x11. And also here, this is just the value of kappa 2. It's going to also be interpolated by a delta measure at the x22. So you see, you can easily pick some interpolatable Schwartz functions, and then you get a family of theta series. So this is good in the sense that means we can easily get a family, and also we have a lot of flexibility here. And but it may also be so good. That means that we need other considerations to help us to narrow down to maybe more canonical choice, because we believe that in order for this kind of constructing p-adic families, usually there should be maybe one very canonical choice. And this case is kind of similar, a little bit similar to the when you construct like a Ziegler-Eisenstein series to construct p-adic functions or Klingon-Eisenstein families. So in that case, you can also kind of put yourself in a certain situation. You can choose Schwartz functions, and then it's going to give you Ziegler-Eisenstein series. And if you choose the Schwartz function in a way like similar like here, then you're going to get a family of Ziegler-Eisenstein series. But still, you need some other considerations to give you a very canonical choice at P. Okay, so next I'm going to talk about how we choose our section at P for constructing the family. So we need some other considerations, and there are maybe two natural ones. So you might want two things. So one is because we're considering Hida families, we talk about ordinary families. So of course you want your section to have nice properties for the action of UP operators. And also after we get this family, we need to have some computation to relate to study the congruence. So you're gonna have to do some computation of some integrals. So then that means we want the section to be convenient for computing relevant local integrals. Okay, so let's first see the UP operators. So I'm gonna fix an isomorphism of the quaternion algebra. So it's split, so it's isomorphic to 2x2 matrices, and then it's isomorphic to the 4-dimensional vector space with the quadratic form given by this matrix 0, 1, 1, 0. And because we know the rank for SP4 and the O4 are both 2, and we know that the UP operators are actually parameterized a pair of integers m1 larger or equal to m2 larger or equal to 0. So the UP operators on SP4 is given like this. So that means first I'm gonna act by a matrix with the powers of P along the diagonal, and then I'm gonna take the average over the unipotent. And so I write it in an integral, but when you act on a basic form, when there is a level, then it's gonna be a finite sum. And also the UP operators for the orthogonal group defined similarly. So again, first something with powers of P along the diagonal, and then take the average over the unipotent. And here actually they are unnormalized, because in order to normalize the UP operators, we need to know the information about the Archimedean component. The weight of the Archimedean components are used to normalize the UP operators. So here we only look at the place P, so we consider the unnormalized ones. So first, if we want good properties for UP operators, so probably the first thing you might want to pick the UP you might want to pick a section such that it is an eigenvector for the UP operators. But in this case, probably it's not gonna be possible because actually the action of the UP operators will change the support of these Schwartz functions. So for example, if we consider the case when the M1 is equal to M2, then we have these following formulas here. If you act on a Schwartz function, then you will see on this part, actually you see that you're gonna have points with smaller and smaller p-adic values coming into the support. And here is an integral condition. You see, we want that to be inside the integral symmetric 2x2 matrix. But actually, this integral condition is not enough to really bound the p-adic values from before. So this part still you're always gonna have smaller and smaller p-adic valuation points of smaller and smaller p-adic valuations coming to your support. So it's probably not possible for us to really directly get an eigenvector for the UP operators. So let's see what we get. So we actually, the choice we make is this one. So we make this choice. So we're gonna make it supported on the integral points. And then I want the x11 to be supported on ZP cross. And I also want the upper 2x2 block supported on GL2ZP. And then I take the value of chi1, chi2 inverse at x11, and then I take the value of chi2 at the determinant of the upper 2x2 block. Okay, so this is the choice, and if you make the corresponding choice at the Archimedean place, you will be able to get a family. And the nice properties with respect to the UP action is the following equivariance property. And if I have the UP operator from the symplectic group acting on this Schwartz function, actually this is essentially the same as the action of the UP operator from the orthogonal group. So we have this kind of an equivariance property for the action of the UP operator. And from this property, then we will immediately see that if I have a theta series with such choice, this choice at P, and if I pair with an ordinary form, on the orthogonal group, and then take the p-adic Peterson inner product on the orthogonal group, this is gonna give me an ordinary form on GSP4. Well, that means if I don't need to apply an extraordinary projector on GSP4 to get an ordinary family. So because of this equivariance property, if I pair with something ordinary, what I get is also going to be ordinary. And the proof of this one is, this theorem is actually first realized that we could have this nice property, and then you just unfold the definitions on both sides and compare them. So the proof is not very tricky, but takes some work to do the comparison of the operator, the actions on the two, on both sides. Okay, so any questions? Okay, so this is the thing about the properties for the action of UP operators. So next, I want to say something about computing the Peterson norm. So why we consider Peterson norm is because we know that in principle, we know the congruence. The congruence between the Yoshida leaves and the other legal modular forms is related to the Peterson norm of the Yoshida leaf, p-adic Peterson norm. And by the Rayleigh's inner product formula, we know that this Peterson norm actually will factorize into a product of local integrals. So the matrix coefficients of the Schwartz function for the wave representation, then times the matrix coefficients of the local representations of the quaternion algebra. And so in the above mentioned works on the Yoshida leaves, actually this Peterson inner product has already been computed when the form is fixed and when at P is the full level. And so here, yeah, but at other ramified places, they also assume some conditions like a square free level to simplify the case. But essentially for us here, what we want to consider kind of different from before is actually the computation at P, because instead of the spherical vector, we're going to use the ordinary vector. And also it's going to be a test for our chosen sections, because if it's a good one, the computation should be doable. If it's a bad one, probably the computation is going to be complicated. Okay, so we computed this one. The local computation at P, and in the case when this pi1 and pi2 are both unramified. And ordinary. At P, and also we assume that the weight of F1 is strictly larger than the weight of F2. And in this case, the above local integral at P is equal to the following. So it's going to be a product of a root of unity. So this root of unity is the scalar coming from the wave representation, and a constant, a scalar. And then times a factor that involves the Satake parameters of pi1 and pi2. And here the alpha I and beta I are Satake parameters. of the local representation of pi I at P. And this factor actually, one can also recognize this factor. This is actually the modified Euler factor for the Rankin-Selberg L function at 1. So this is also kind of something expected to show up, because when you do the p-adic interpolation for families, usually what you need is to change the Euler factor at P to the modified Euler factor at P conjectured by Coates and Pyron. And so somehow we computed this integral and get what we expected. And so in this computation, actually, the difference is we need to consider the ordinary vectors here. So we need to consider the matrix coefficients attached to ordinary vectors. So for unramified spherical vectors, we have very nice formulas for the matrix coefficients, so we can easily use for computation. But actually, the matrix coefficients for the ordinary vector is not so nice. So it's nice on some cells, and some other cells is not so nice. And actually, what we do here is actually we use the equivariance property of the section. So here it's kind of you do an ordinary projection to this spherical vector. So we use the equivariance property to move that ordinary projection to the symplectic group. So it's gonna be the ordinary projector is kind of moved to the symplectic group. Then therefore the action on the symplectic group is not gonna change the level of the orthogonal side. So then we'll use the matrix coefficient for the unramified sections to do the computation in this way. It kind of simplifies the computation for this integral. And yeah, that's the main idea in this computation here. And I think I'm gonna stop here. I think I have finished what I plan to say. And thanks for listening.
Okay, so let's thank the speaker. Are there any questions?
I'm wondering whether the property of finding a test function, Schwartz function, that is a UP has the same, where the UP operator for the orthogonal group is related to the UP operator for the symplectic group, whether that can be done, for example, for unitary group theta correspondences in general, because if you can do that, then you can probably construct square root p-adic L functions in great generality.
We haven't thought about unitary groups, but actually we have a constraint here. So to have this, actually, we want the size of the groups actually match. So in this case, the rank is equal. So their UP operators are both parameterized by the same number of integers. So when they don't match, there is gonna be, we haven't really looked into it, but probably something different thing will happen when the rank does not match.
I was thinking of the case where the ranks match.
When the rank match,
for you, two unitary groups of the same size, different signatures.
Yeah, I think we really need to look at the case. So it's possible. Maybe it's possible, but we really haven't thought about that.
Right.
But yeah, but thanks for bringing this up. So maybe that's a direction maybe we want to look at.
So at the end, do you get congruences between Yoshida lifts and other forms, or is that work in progress still?
Oh, it's still in progress. So there are several steps. So first we get the family, and then we do the Peterson norm, and then we need to relate the Peterson norm to the congruence. And for that step, actually, it's gonna be another different type of computations. We need to pick some other forms, so usually not an eigenform, but integral over the GSP4, and to pair with this Yoshida lift. And then if you want to, then the Peterson norm will show up in the denominator, and actually the denominator you expect to be kind of gives you the congruence, because when you spectrally decompose a form, if it's congruent to something, then it's something we're going to show up in the denominator. So therefore, we need to still control the numerator. So first you need to pick a nice form so that you can see what the numerator is. And so in the previous case, the form that picked is the restriction of the Ziegler-Eisenstein series from GSP8. And the one shows up is the standard L functions. And so they need to assume some conditions, like the mod p non-vanishing of some values of the. So you have the flexibility to pick the Ziegler form, so you can get the special values at different critical points. They need to assume some conditions for some of those critical points, maybe mod p non-vanishing, so that the congruence is really given by the denominator, which is the Peterson norm. And yeah, so that's another step, and that step is we're still working on that.
So the expectation is that if P divides that Rankin-Selberg special value, then you do get a congruence mod P. That's where you're headed?
Yeah.
Okay, thanks.
Any questions or comments? Okay, if not, let's thank the speaker again.